The research paper investigates the stability of solitons in a 3D Maxwell Lorentz system with an extended charged spinning particle. The solitons are solutions representing a particle moving with a constant velocity and rotating with a constant angular velocity. The authors focus on the orbital stability of moving solitons with zero angular velocity and the linear orbital stability of rotating solitons with zero velocity. The Hamilton Poisson structure of the Maxwell Lorentz system is degenerate and admits Casimir invariants. A Lyapunov function is constructed as a linear combination of the Hamiltonian and a suitable Casimir invariant, with a key lower bound achieved through angular momentum conservation and spectral arguments. The paper's structure includes sections on the Maxwell potentials, the Hamilton Poisson structure, the canonical transformation to the comoving frame, the reduced system, the solitons, the Lyapunov function, orbital stability, angular momentum conservation, the stability of the linearized dynamics, and the positivity of the Lyapunov function. The authors also provide comments, discuss soliton parameters, and consider the density of C∞0 in the space of divergence-free vector fields. This research paper investigates the mathematical analysis of the Maxwell Lorentz system, a fundamental model in classical electrodynamics that describes the motion of a charged particle coupled to its own electromagnetic field. The system, introduced by Abraham in 19,031,905, allows for the avoidance of ultraviolet divergence, and has been instrumental in the discovery of the mass-energy equivalence. The paper focuses on the long-time behavior of the system, particularly the orbital stability of solitons, which are solutions moving with constant speed and rotating with constant angular velocity. The authors assume a smooth, spherically symmetric, and non-identically zero charge density, and explore the invariants of the system under the Euclidean group generated by translations, rotations, and reflections of the space R-cubed. The main results of the paper are the orbital stability of solitons with velocity less than 1 and the linear orbital stability of solitons with zero total momentum. The approach relies on the Hamilton Poisson structure of the system, which was constructed in a previous work. The proof of orbital stability involves reducing the system to a comoving frame and establishing a lower bound for the Hamiltonian as a Lyapunov function. To prove the linear orbital stability, the authors employ conservation of angular momentum and construct a Lyapunov function for the linearized equations as the sum of the quadratic part of the Hamiltonian with the Casimir functional. This strategy is an analog of the energy Casimir method. The conservation of the Lyapunov function is proved, and a suitable lower bound is established using spectral arguments, including the Heinz inequality from interpolation theory and the closed graph theorem. The paper also discusses related work in the mathematical theory of the Maxwell Lorentz system, including the establishment of conservation laws and the Hamilton least action principle. The authors comment on open questions and future directions in the field, highlighting the significance of their results in understanding the behavior of charged particles in classical electrodynamics. In the context of classical electrodynamics, the Maxwell Lorentz system describes the interaction between a charged particle and the electromagnetic field. The system consists of three equations: the Maxwell equations for the electromagnetic field, the Lorentz equation for the motion of the charged particle, and the continuity equation for the charge density. This paper focuses on the stability of solitons in the Maxwell Lorentz system with a spinning particle, where solitons are solutions that maintain their shape over time and move with constant velocity. The authors use the Coulomb gauge, which allows them to eliminate the gradient of the scalar potential from the equations. They also apply the Wiener condition on the Fourier transform of the charge density, enabling the use of the Wiener-Tauberian theorem. This method was first introduced in the study of the system of a particle coupled to a scalar wave field. The paper presents several key results, including the global attraction to stationary states and the asymptotic stability of the solitary manifold for the 3D and 2D Maxwell Lorentz systems without spinning. Additionally, the adiabatic effective dynamics of solitons for the 3D system has been proven. For the Maxwell Lorentz system with a spinning particle at rest, the global convergence to rotating solitons has been established. The authors define the spaces of real functions ck, h's, and h1, which are used to describe the properties of the solutions to the system. They also introduce the Hilbert spaces f0 and f1, as well as the space Y, which is the product of these spaces and additional spaces for the particle's position, momentum, and angular momentum. The main result of the paper is the proposition that for any initial state, the system admits a unique solution that is continuous in time and belongs to the space Y. Furthermore, the map W, T, that maps the initial state to the solution at time t is continuous in Y for every time t. The energy and momentum of the system are conserved, and the system exhibits a global attraction to stationary states. The paper concludes by discussing the well-posedness of the system, which is essential for understanding the behavior of the solutions. The authors have successfully bridged the gap between complex research and concise summaries, providing a clear and precise overview of their findings for expert audiences. In the context of the Maxwell-Newton system, the Hamilton Poisson structure is derived and utilized to establish a Hamiltonian representation for the system. The Hamiltonian functional, H, is defined as the sum of kinetic and potential energies, and it is well defined and Frechet differentiable on the Hilbert phase space Y. The system then admits a Hamilton Poisson representation, with the skewsymmetric structural operator J, Y, given by a matrix. This representation consists of four equations describing the evolution of the electromagnetic field, the position, the momentum, and the angular momentum of the particle. The system also possesses Casimir invariants, such as pi squared, which are conserved quantities under the Hamiltonian flow. To transform the system into the comoving frame, the fields are redefined as A, Y, T, equals A, Q, T, plus Y, T, and pi, Y, T, equals pi, Q, T, plus Y, T. The transformation map T is introduced, which changes the variables in the system via the mapping, A, pi, Q, P, pi, right-pointing arrow, A, pi, Q, P, pi. The conserved total momentum P is expressed as P integral, pi, nabla A, dx, using the identity, 2.6. This transformation allows for a more convenient analysis of the system's behavior in the comoving frame. In the context of a Hamiltonian system, the transformation T, A, Q, omega, right-pointing arrow, A, Q, omega, is introduced to simplify the analysis of the original system, 3.3. This transformation leaves the Lagrangian actions unchanged and thus preserves the solutions of the system. The Hamiltonian H, A, pi, Q, P, pi, is defined in terms of the transformed variables, leading to a reduced Hamiltonian system with parameter P element of R cubed. The reduced Hamiltonian HP, A, pi, is well defined and Frechet differentiable on the reduced phase space Z equals F circled plus R cubed. The system, 4.5, reduces to a family of Hamiltonian systems with parameter P, which are equivalent to the original system, 3.3. The equations for Q and P in the reduced system, 5.1, correspond to the conservation of the conjugate momentum P. The solitons of the system, 3.1, are calculated, which are solutions of the form SV, omega, T, equals, avenue, omega, x vt, pi v, omega, x vt, vt, pv, pi v, omega. The second line of 3.1 and the definition 2.7 imply that PV equals MV plus and B nabla acately TAV omega y rho y and B nabla acat nabla I HT and pi v omega equals I omega plus and B nabla acately tie and avenue omega Q plus y rho y and B nabla acat nabla I HT. The corresponding conserved, total, momentum is given by 2.10 PV, omega equals, and B nabla acately, T pi V, omega, nabla asterisk operator avenue, omega, T, and B nabla acat nabla I, HT plus MV plus, and B nabla acately, T rho, Y, avenue, omega, Y, and B nabla acat nabla I, HT. In the comoving frame, solitons become stationary solutions of the reduced system. The first two equations imply that increment avenue, omega, y, minus, v nabla, second avenue, omega, y, equals minus j, y, T, which, on the Fourier transform side, yields AV, omega, k, equals V minus k, Vk, k2 minus I omega logical and nabla, rho, k. The conditions imply avenue, omega element of F1, pi V, omega element of F0 for V, less than 1, omega element of R3. For V is greater than or equal to 1, avenue, omega, nay, Asian/element of F1, so corresponding solitons do not exist. The last equation in 3.1 is equivalent to the relation pi V, omega, ba nabla dBl omega, which holds if and only if V, omega, element of sigma. The soliton's effective moment of inertia if is defined, and its existence and uniqueness are ensured. The total momentum admits a representation PV, omega equals MEF, V, omega, V. The orbital stability of solitons is defined in terms of reduced trajectories, and a Lyapunov function is constructed to prove stability. For ρ, x, is defined as 0, all solitons are orbitally stable. The research discusses the stability of solitons in a mathematical framework, focusing on the Hamiltonian structure and its properties. It starts by defining the Hamiltonian delta HV, omega and its components, including terms related to the curl and divergence of the vector fields. The authors then derive a lower bound for delta HV, omega, which is crucial for establishing orbital stability. In the case where omega equals 0, the Hamiltonian HV, 0 is used as a Lyapunov function, and a lemma is proved to demonstrate the lower bound. This leads to the theorem on orbital stability of solitons with omega equals 0. The methodology involves a combination of mathematical derivations, using equations and inequalities, to arrive at the stability result. The technical details are dense, involving concepts like curl, divergence, and the properties of vector fields, making it essential to have a strong understanding of these topics to appreciate the summary. The research paper discusses the conservation of Hamiltonian's principal part and the angular momentum for a system with zero total momentum. It begins by establishing that the map V, maps to right-pointing arrow PV, 0 is a homeomorphism, which leads to the conservation of HP, Z, T, for the system. The lower bound on HP, SP plus delta Z, minus HP, SP, is derived, and combining this with the previous result, it is shown that sub T element of R, ba nabla dBlz, T, minus SV, 0, ba nabla dBlz right-pointing arrow 0 is epsilon right-pointing arrow 0. The paper then introduces the Lyapunov function lambda V, omega, Z, for the reduced system, which is an invariant and has the solitons SV, omega as its critical points. The angular momentum conservation is discussed, and it is shown that the stationary solutions are the solitons SV, omega with V equals 0. The Hamiltonian for the system with P equals 0 is also presented, and the set Z infinity. 0 is dense and Z. The paper concludes with a lemma stating that for solutions to the system with initial states INZ infinity 0, the Hamiltonian's principal part and the angular momentum are conserved. Here is a combined summary of pages 17 and 18. The authors establish the stability of solitons S omega for the nonlinear system, 9.3, by exploiting the angular momentum conservation, 9.4. This conservation suggests a lower bound of type, 7.1, on the manifold M omega defined in 9.8. However, the manifold M omega is not well defined on the phase space Z. Instead, the tangent space T omega is defined as the set of delta Z element of Z satisfying E omega n delta Z equals 0, where E omega n is defined in 9.9. This tangent space is a closed linear subspace of codimension 3 in Z0. The authors then define the Hilbert space T0 omega as the closure of T omega intersection Z0 in Z0, endowed with the norm of Z0. The space T0 omega admits the representation, 9.9, with delta Z element of Z0 and is a closed linear subspace of codimension 3 in Z0. The orthogonal projection P omega of Z0 onto T0 omega is defined in 9.13. To study the stability of the linearized dynamics in the tangent space, the authors linearized the reduced system, 9.3, at the soliton S omega. The variational equation is obtained by replacing z, t, with z, t, plus xi, t, and keeping the terms linear in xi, t. The linearization of 10.1 at the soliton is given by 10.3. The corresponding Hamilton Poisson structure for the linearized dynamics is calculated, and the quadratic part of h0, s omega plus xi, is replaced by h omega, xi, defined in 10.5. The last linear term in h omega, xi, contributes only to the equation for gamma, t, which is given by 10.6. After simplification, the linearized equation becomes 10.7. This equation describes the linearized dynamics in the tangent space and is crucial for studying the stability of solitons S omega. The linearized equation for the system, as described in equation 10.3, is derived, and it is proven that the tangent space T omega is invariant under the linearized dynamics. This is achieved through the proof of lemma 10.1, which shows that the vector field df S omega xi is tangent to T omega. The stability of the system is then established through theorem 10.2, which proves the existence and uniqueness of solutions within T omega and provides an a priori estimate for the solution's norm. This estimate is derived using the conservation of an appropriate energy functional, specifically the quadratic part of the Lyapunov function 10.13. The functional's conservation under the linearized dynamics is demonstrated, leading to the uniform bound 10.12. The paper also presents a lower bound for the Lyapunov function on the tangent space, which is a crucial step in establishing the stability of the system. This is achieved through the proof of proposition 10.3, which shows that the Lyapunov function admits a lower bound, as expressed in equation 10.15. Here is a combined summary of pages 21 and 22 of the research paper. The operator Q rho is self-adjoint in Z with domain D, and its difference with Q is a bounded finite rank operator in Z. The common domain of both operators contains the space Z infinity, which is dense in Z. Proposition 11.1 states that Q rho is non-negative and has a kernel of dimension 3, with the kernel intersecting T omega being 0. The proof of proposition 10.3 involves restricting the quadratic forms xi, q prescription, and xi, q xi, onto T infinity omega and denoting the corresponding non-negative self-adjoint operators as Q rho and Q. Lemma 11.2 shows that Q rho micro Q with sufficiently small micro greater than 0, which is essential for establishing the bound 11.2 with kappa equals micro. The Heinz inequality is applied to obtain the bound 11.8 for all S element of 0, 1, implying that Q's rho micro SQs. This, in turn, implies the bound 11.2 with kappa equals micro. Remark 11.3 notes that proposition 11.1 eliminates the point spectrum at 0 of the operator Q rho in the tangent space T omega. But this fact alone does not imply the bound 11.1, due to the presence of the continuous spectrum of Q rho. The positivity of the Lyapunov function on the tangent space is proven in proposition 11.1, which is essential for establishing the non-negativity of the operator B. The form B, y, can be written as y by, for y element of y infinity, where B is an operator defined in 12.1. Proposition 11.1i follows from lemma 12.1, which shows that the operator B is non-negative. The proof of lemma 12.1 involves considering B as a self-adjoint operator in Y with domain D, B, and showing that the resolvent R, lambda, equals B minus lambda, Y is a bounded operator for lambda less than 0. The calculation of the kernel reduces to a finite-dimensional problem, and the equation, B minus lambda, Y equals 0 is solved to establish the non-negativity of B. Here is a combined summary of pages 23 and 24. The equation, 12.5, is rewritten, and its Fourier transform is taken, resulting in equation, 12.6. The vector field $m caret, x, rho, x, w is divergence-free due to spherical symmetry, 1.2. Substituting 12.6 into the second equation of 12.4 yields equation 12.7, where the matrix A lambda, is Hermitian for lambda is less than or equal to 0. The quadratic form of A, lambda, is derived, and it is shown that the matrix A, lambda, is scalar, leading to equation 12.8. This equation holds since A underscore 0 equals A plus 0, which is equivalent to equation 12.9. The proof of proposition 11.1 is provided, where the non-negativity of Q rho follows from lemma 12.1. The kernel of Q rho is characterized, and its dimension is shown to be 3. The intersection of the kernel of Q rho and the tangent space T0 omega is shown to be 0. The authors provide several comments on their results. They note that the lower bound on the quadratic form Q rho implies a similar bound on the tangent space for the Lyapunov function lambda 0, omega, but this does not provide stability for the nonlinear dynamics. They also explain their method of proof for theorem 10.2, which reduces the problem to calculations with differential operators. The orbital stability of solitons SV, omega with omega, nay, ation/equals 0 and v less than 1 for the nonlinear dynamics remains an open question. Finally, the authors prove lemma 6.2, which provides a formula for the soliton parameter pi v, omega. They consider two cases: omega parallel to v and omega perpendicular to versus in the first case, they derive equation b.2, which is used to obtain equation b.3 for pi v, omega. In the context of the paper, we are discussing the case where omega and v are orthogonal vectors. The Fourier transform of A, denoted as A, k, is perpendicular to k for any k in R³. This implies that A, k, equals k in A, k, with A, k, equals k in A, k, k squared. We then define a sequence of functions bm, k, and bm, k, which converge to A, k, and A, k, respectively in L squared as m tends to infinity. This sequence is used to construct a sequence of functions am n in C infinity that converges to a in L squared as n tends to infinity for every m. Consequently, we can conclude that C infinity is dense in the Hilbert space F, which consists of divergence-free vector fields A in L squared. The paper also references various works in the field of fluid and plasma equilibria, geometric mechanics, and symmetry, as well as the stability theory of solitary waves in the presence of symmetry. Furthermore, it discusses the coupled Maxwell Lorentz system and its soliton-type asymptotics, along with the scattering theory and adiabatic limit for a rotating charge coupled to the Maxwell field. The mathematical techniques employed include the use of spherical coordinates, differential geometry, and the theory of Lie groups. The paper highlights the importance of the Pauli-Fierz model of classical electrodynamics, which is a fundamental model in the study of classical radiation theory. It also cites works on the stability of solitary waves for nonlinear Schrödinger equations and the non-relativistic quantum electrodynamics, emphasizing the mass renormalization process. The paper's main contribution lies in its novel approach to the classical radiation theory, leveraging the mathematical framework outlined above. It presents a comprehensive analysis of the stability of solitary waves and their asymptotics in the context of the coupled Maxwell Lorentz system. The work also touches upon the adiabatic limit for a rotating charge coupled to the Maxwell field, providing a detailed mathematical treatment of the subject. In conclusion, the paper presents a thorough examination of the classical radiation theory, utilizing advanced mathematical techniques and referencing seminal works in the field. It provides a rigorous analysis of the stability of solitary waves and their asymptotics, contributing to the ongoing research in this area. The research presented on pages 27 and 28 focuses on the dynamics of charged particles and their radiation field, particularly in the context of classical electrodynamics. It draws from various mathematical and physical theories, including the works of V. Imaiken, A. Komech, and H. Spohn. The authors discuss scattering asymptotics, Lagrangian theory for rotating charges, and invariants for the Poisson equations, among other topics. They also reference key works such as Jackson's Classical Electrodynamics and Cato's Notes on Some Inequalities for Linear Operators. The pages highlight novel ideas in the field, including the concept of attractors for nonlinear Hamiltonian partial differential equations and the Hamilton Poisson structure for the Maxwell Lorentz equations with spinning particles. The author's work contributes significantly to our understanding of the dynamics of charged particles and their radiation field, shedding light on the behavior of particles in various scenarios.